Hello everyone, I'm Amber Pal, and today I'll be talking about our recent work understanding noise-augmented training for randomized smoothing, which will appear in the Transactions of Machine Learning Research this month. This is joint work with Jeremiah Sulam, and we are both at Johns Hopkins. We'll work in the setting of binary classification over a domain scriptx, where the learning task is to differentiate these orange dots from these blue crosses. Given this task, you might learn a function f that predicts 1 in the orange regions and 0 otherwise. In this talk, I won't focus on the learning aspect of this problem too much. So you can think of f as being the base classifier for this task. In this setting, let me define an adversarial example for x to be any x prime epsilon close to x, such that my predictor changes its prediction from x to x prime. Existence of such low norm adversarial examples poses a grave threat for current machine learning algorithms, because you can have cases like this where a slightly perturbed stop sign is completely misclassified to be a go sign. Now, randomized smoothing is a recent and very popular technique to robustify any existing classifier against such adversarial examples. So let me explain how it works. Given this classifier on the left, randomized smoothing will produce this classifier G on the right, which, as you can see, has these smoothed decision boundaries. How does it do it? Well, given any input point, this red point here, randomized smoothing takes the average of f over a small local neighborhood around that point. And you do this for every input point to get g, which is defined to be 1 whenever the average of f around x according to q is at least 0.5 and 0 otherwise. Now, with that context, I can now formalize what I mean by robustness in our context. The robustness certificate at any black point x is defined to be the radius of this yellow ball, where the output of f remains constant, which is 1 in this case. Now, as you would expect, for most x, the robustness certificate would increase when you perform randomized smoothing. Now, how do you quantify this? Well, the radius of this yellow ball can actually be computed in closed form for any f for some specific smoothing distributions. For instance, for the standard Gaussian distribution, the radius of this ball is proportional to the variance of the distribution. Now, that is all well and good, except it doesn't work that well in practice. For modern networks, the smooth classifier performs very poorly in practice. And this is commonly attributed to the fact that the network was not trained with noisy data to begin with. To remedy this, a common trick that is used is noise-augmented training, which, as you might expect from the name, is that instead of learning from the clean data, you first of all perturb each data point with some additive noise V sampled from some distribution Q alpha, and then find the classifier f prime, which obtains the minimum error on these noisy data points. Then we proceed as we did earlier by applying randomized smoothing to f prime with this distribution Q beta to obtain the final classifier G. Now, in accordance with common intuition, Q alpha is taken to be equal to Q beta. However, these tricks are not very well understood in practice. And that is where this paper comes in. The central question that we study is, what is the effect of Q alpha and Q beta on the risk of this final smooth classifier G? For the rest of this talk, Think of Q alpha and Q beta as standard Gaussian distributions with variance alpha and beta respectively. And hence alpha and beta can be thought of as the strengths of data augmentation or randomized smoothing respectively. The full results, which are derived for much more general single parameter probability distributions, can be found in the main paper. Alright. We need a little bit of setup before we go into the main results. First of all, we define G alpha beta to be the classifier obtained by first training with Q alpha and then smoothing with Q beta. The risk of G is defined in the standard sense, which is the expected error over the data distribution. Now, the excess risk is defined as the increase in risk after we train F with noise augmentation and randomized smoothing. Now, importantly, noise augmentation is defined to be beneficial if there exists a choice of alpha and beta such that G has lower excess risk, that is delta alpha beta, than if we did not use any noise augmentation, that is delta 0 beta. Okay. Note that alpha is 0 here, which means that there is no noise augmentation. Here's an informal overview of the main theoretical results before I delve into the details. We identify a separation parameter, zeta, of the distribution which controls exactly whether noise augmented training is going to be beneficial. Pictorially, this looks like the following. So in this picture, recall that these orange regions are the regions where fx is equal to 1. Now in this picture, the orange regions are far apart and the black arrows have a large average length. We call this regime the large interference distance regime. And in this regime, we can show that noise augmentation is not beneficial. On the other hand, when these orange regions come closer and the average distance gets smaller, we move into the small separation regime. And in this regime, if you tune the alpha and beta properly, then noise augmentation can be beneficial. With that, here is the first main result. Define zeta f as the lower interference distance of f to be the minimum distance between the orange regions where fx is equal to 1. Then our theorem 1 says that there exists a class H1 such that for each member of this class, f has a large lower interference distance and training with noise is not beneficial. Here is the intuition behind the proof. So when the partitions are well separated in the input space, noise augmented training shrinks those partitions. And randomized smoothing further shrinks those partitions, leading to a situation where we have much worse risk than we began with. Now you might wonder, is this behavior only true for these very specific distributions that I'm showing on these slides? Surprisingly, no. In fact, we can show that for any f with bounded support, there exists an upper bound on the excess risk. And this upper bound is increasing in both the noise augmentation strength alpha and the smoothing strength beta. This suggests that without additional restriction on the data distribution, noise augmentation is never a good idea. By the way, this bound is tight for all the functions in H1 on the previous slide. Now you might be wondering, wait. You said that people use noise augmentation in practice, right? Well, indeed, noise augmentation seems to be beneficial in practice. Specifically, let's dig a little bit deeper and plot the excess risk for MNIST for various choices of beta. The first thing that we see in this plot is that alpha positive has always lower risk than alpha equals 0. Additionally, alpha equals beta is not the best choice in general. Specifically, if you look at this highlighted plot line, beta is 0.8, whereas the best alpha that you could choose was 0.6. Now this leads to a conjecture that real data distributions seem to have small interference distance, zeta f, and hence they seem to not lie in the regime that is covered by theorem 1. And so the natural question is, can we formally characterize such cases where noise augmentation is beneficial? And since I'm showing this, yes, we can. For this, I'll need a slightly different definition of interference called the upper interference distance, this time defined to be the max of the distances between the orange regions. With that, our last main result will show that there exists a class of functions H2, so that for each member in this class, f has a small upper interference distance, so the orange regions are close, and training with noise is beneficial. The proof in this case is interesting and nuanced. The intuition is that when the partitions are close, their interactions can be used to deform them. And finally, randomized smoothing can be used to further lower the risk of the noise-augmented classifier. Alright. I'll now conclude. In summary, we have found a separation parameter of the distributions that determines whether noise augmentation is beneficial. At high separation, noise augmentation is not beneficial. At low separation, noise augmentation can be beneficial if you set the beta and the alpha properly. Finally, another interesting fact that also falls out of our analysis is that the training noise need not be the same as the smoothing noise beta for best performance. With that, here is a QR code linking to the main paper. You can also find the link in the video description. Thanks for listening.